Welcome to this video. In this video we will compute the Thevenin equivalent resistance, which is the Thevenin equivalent circuit, of a circuit with one dependent source. So the circuit is drawn on top. It turns out to be a small signal model for the common emitter amplifier, which is shown at the bottom. And you'll notice that we have opened up the circuit on the left. So the idea is we want to find out what a source, if I were to connect a source to it, we want to find out what the equivalent resistance is that the source would see. This would be the Thevenin equivalent resistance. Now if you look at the small signal model, I have no independent sources, but I do have one dependent source. So what I will need to do is find the Thevenin equivalent resistance by applying a test source, either a current or a voltage source, finding the resulting voltage or current, and using that to compute the Thevenin equivalent resistance. So let's go ahead and do that. We'll bring up a picture of just the small signal model, and what I want to do then is add a test source. In fact, here we'll do this in a bright red color. So I add a 1 volt test source, and then what I need to figure out is the current that goes into the circuit as a consequence of this 1 volt source. And my Thevenin equivalent resistance will be the 1 volt divided by this current. Again, just to make sure it's clear, the Thevenin equivalent circuit, since I have no independent sources, is just going to be a single resistor. So all we need to do is figure out what the current is when I apply this 1 volt source. Seems like it should be fairly easy, but we'll see how it goes. We notice, well, and to solve this, we'll probably be best off to apply Kirchhoff's current law to this node here. Yeah, we'll try it and see how it goes. So, and we'll also notice that this I is equal to I sub B. So if we can find I sub B, then we found I and we can find RTH. So let's start by writing an unknown voltage across the resistors in the current source, and we'll call this, say, V0. And in terms of V0, we can then say that the current that goes through this 2 k ohm resistor, we'll call this I2, as well as the current that goes through this 2 k ohm resistor. Since they have the same voltage across them and they're 2 k ohms, it'll be the same. I can write I2 as V0 over 2 k ohms. So now, applying Kirchhoff's current law, we have the current coming in here is I sub B. The current coming in here is 50 I sub B. The current leaving is I2 plus I2. And we can then simplify this equation to 51 I sub B is equal to 2 times V0 over 2 k ohms. This we get this by substituting the V0 over 2 k ohms into I sub 2 here and here. Okay, now the last thing we need to do is come up with an expression for I sub B, which we can get by noticing that if we have a 1 volt source here, the voltage across the series equivalent of the 1 k ohm and the 50 ohm is given by 1 volt minus V0. So we have then I sub B is equal to 1 volt minus V0 over 1 k ohm plus 50 ohms, which is 1.05 k ohms. So now we can combine this equation and this equation to get the following. 51 times I sub B, which is 1 volt minus V0 over 1.05 k ohms is equal to 2 V sub 0 over 2 k ohms. And we can solve this equation for V0. When we do that, we get 2 V0 over 2 k ohms plus 51 V0 over 1.05 k ohms is equal to 51 over 1.05 k ohms. And let's see, we can solve this now for V0 without going through all of the details. Let's see if I can get this right. We're going to have V0 is 51 over 1.05 k ohms divided by 2 k ohms plus 51 divided by 1.05 k ohms. And that gives me then V0 is 0.97, well actually let's call it 0.980 volts. Okay, well, we're almost done. We can take this expression, in fact, we'll change colors here just to make it clear what we're doing. We can take this expression, plug it into here, and figure out what IB is. So here we have, in fact, why don't we clean up a lot of this mess. We have then that IB is equal to 1 volt minus 0.980 volts. That's this 1 volt minus V0, and V0 is given by this, divided by 1.05 k ohms, which when I work, I get that IB is 1.90 times 10 to the minus 5 amps. Okay, I could call that 19 microamps. With this, I can now compute RTH. It's 1 volt over 1.90 times 10 to the minus 5 amps. That's this value, which gives me let's see, this gives me 52.5 k ohms. Okay, so basically by applying this test voltage and finding the resulting current that goes in, we've discovered that the Thevenin equivalent resistance of the circuit is 52.5 k ohms. So let's see if we have time to work it the other way. Okay, so let's, instead of putting in or attaching a test voltage source, let's attach a test current source and put 1 amp in, and then see what the voltage from across the source would be. And this will then tell us what the this will tell us what will this tell us? This will tell us what the Thevenin equivalent resistance is. Okay, and to make things go faster, I'm going to combine these two resistors, these two 2K ohm resistors in parallel, and replace them by a single 1K ohm resistor. That's the equivalent resistance. So this is 1K ohm. Okay, so if I look at the way things are set up then, I sub B is equal to 1 amp because all of the current that flows through here also comes from the source. So we have then I sub B is 1 amp. We can apply Kirchhoff's current law, and let's define this as an I1. And so the current flowing into the node is I sub B plus 50 I sub B. The current flowing out is I1. So that says that I1 is 51 I sub B, which is 51 amps. Okay. Now the voltage V, this will be the voltage across these two resistors plus the voltage across this 1K ohm resistor. So the voltage across the 1K ohm resistor, let's call this V1. V1 is 51 amps times 1K ohm, which is 51 kilovolts. This is a pretty large voltage. The voltage, let's call it VB, this voltage here, is going to be 1 amp, IB, times 1.05 K ohms, which is 1.05 kilovolts. So that means that the total voltage V is going to be V1 plus VB, which is 52.05 kilovolts. And the Thevenin equivalent resistance, RTH, is going to be this 52.05 kilovolts divided by my 1 amp that I put in, which gives me 52.05 K ohms. So that is close to the answer I got before, but somewhat different. I wonder if I've made a mistake somewhere. I hope not, because I've only got 1 minute and 4 seconds to find it. If I've made a mistake, I would actually suspect it would have been here. And in fact, I wouldn't be surprised that the difference is because I rounded this guy off to 3 digits and then I subtracted this from 1 volt. So I'm assuming that my difference of 0.2 here is not exact, which is probably where I get the 52.5 here and the 52.05 here. This one I believe is exact because I didn't do any rounding in the computations. So anyway, that's how I compute the Thevenin equivalent resistance in a circuit that has only dependent sources. I use a test voltage source or current source and find the either current or voltage and compute the Thevenin equivalent resistance from that. So with that, we'll end this video.